let's now consider some common BGP routing issues. And some of these routing issues are similar to those that we had with OSPF and EIGRP. For example, we might have an incorrect network statement. Let's double check to make sure that we've entered the network statement correctly. Let's make sure we haven't transposed a couple of numbers in the IP address as an example. But something that's a bit more unique to BGP is the concept of the next hop router. A big point to keep in mind is that when an advertisement comes into an autonomous system and is advertised over iBGP connections to routers all belonging to the same autonomous system, by default, the next hop router information is not updated. And it's possible that we've got a router residing in this autonomous system that has no way to get to the next hop address that's been advertised to it in this BGP advertisement. One way we could address that is to redistribute BGP into an IGP. We could alternately set up a static route to tell the router how to get to that next hop address. However, we could go into the BGP router configuration of a router and say neighbor, and then we give the neighbor's IP address or peer group name, and then we say next-hop-self. Next hop self is going to cause a router to advertise its IP address as the next hop IP address when it's sending a BGP routing update to an iBGP neighbor. Those are a few different ways we might be able to address an issue where a router within an autonomous system is not able to reach the next hop router advertised in the BGP advertisement. Similar to EIGRP, we could have a split horizon issue, which says if a route was learned on an interface, that interface is not going to advertise the route back out. And in a point-to-multipoint network, maybe like frame relay, that could be an issue. We could have filtered routes. We might be doing some route filtering, maybe intentionally, maybe inadvertently we've filtered out specific routes, or maybe there's a more believable route, like a static route in the IP routing table, and that's the route that's being used as opposed to the BGP learned route. And in our last video, we talked a lot about the BGP path attributes. We talked about the different ways that BGP could make a path selection decision. Well, it's possible that BGP is taking a suboptimal route because of inappropriate path attributes. In fact, to illustrate that a bit further, let's go out to a live interface right now and troubleshoot a very real-world issue, an issue that I've personally experienced, where you've got an enterprise network connecting out to more than one ISP, and by default, we're taking a suboptimal path, and let's see how to fix that. I remember back in the 1990s, I was working at a university, and the university had a couple of connections out to the internet. And back in those days, bandwidth was not as available as it is today. I remember we had a 10 meg link out to one ISP, and we had a T1, a 1.544 megabit per second link out to another ISP. And we had a BGP peering relationship with each of those ISPs. Unfortunately, we were using by default the lower speed link to get out to the internet. And hosts out on the internet that were coming into the university, they were using the lower speed link. And the reason was, the ISP that had the T1 link, it was closer to the internet backbone. We had a fewer number of autonomous system hops in almost every case if we used that ISP. And to fix that, we had to do some BGP path attribute manipulation. And that's what we're going to do here with this topology that you see on screen. Notice that router R2 has a connection, a 768K connection out to ISP1. It's got a 1.544 megabit per second connection out to ISP2. And clearly, we would prefer to use the ISP that had the highest bandwidth. We would prefer to use ISP2. Let's see what we're using right now, though. If I do a show IP route on router R2, how do I get to a network out on the internet? I'm using a 9.9.9.9 as an example of some internet destination. That's actually a loopback interface on my iNet router on screen. And it looks like to get there, I'm going to go via this router. I'm going to go via 198.51.100.2. That's actually ISP1. That's the slower link. Why is that? Well, let's take a look at our BGP table. I'll do a show IP BGP. BGP knows about two different ways to get there. It knows that we could get there via ISP2 or ISP1, but notice the greater than sign. This is telling us that we're using ISP1. And that's this enterprise network, Autonomous System 65001, as it's going out to the internet. How does it look from the internet coming back in? Well, let's go to the internet router and let's do a show IP BGP, and let's look at one of the routes inside of the enterprise autonomous system, 192.0.2.0 as an example. I could get there a couple of different ways. But notice where the greater than sign is. It looks like from the perspective of the internet, we're going to go via ISP1. Again, we're going via the slower link. And the underlying cause is most likely a lower router ID. And in the real world, we're probably not going to be able to do any work on the ISP router. We have to do our work on our enterprise router. In this case, router R2. And we want to be able to do configuration just on R2 to influence both outbound and inbound path selection. To influence the outbound path selection, let's use the local preference. Notice that we do not currently have a local preference set for routes that we've learned via the ISP1 or ISP2 routers. Let's change that. And let's remember that higher local preference values are preferred. To do this, we'll create a couple of route maps. Let's go into global configuration mode, and I'll say route-map, and I'm going to create a route map for ISP1. And I'll set the local preference to 100, and I'm going to apply this to routes that I'm learning from ISP1. Let's create another route map for ISP2, and I'm going to set a higher local preference value to make it more preferable. I'll make it 200. Now, to make this take effect, I have to apply the route maps as part of a neighbor statement in router configuration mode for BGP. Let's go into router BGP configuration mode for our autonomous system of 65,001. And let's give the neighbor statement for ISP1. I'll say neighbor, and the IP address is 198.51.100.2. And to that neighbor, I want to apply the route map of ISP1. And I want to apply that in the inbound direction. In other words, as I learn routes from that neighbor, I want to apply the ISP1 route map, which is going to assign those routes a local preference of 100. Let's do something similar for the other neighbor for ISP2. Let's update the neighbor IP address. It's got a 6 in the last octet, and we'll apply the ISP2 route map. To make this take effect, let's reset the BGP process. I'll do a clear IP BGP star soft. That's a little less intrusive. And we'll do a show IP BGP. And look at this. Now, in order to get to this 9.9.9.9/32 network, we're going to go via ISP2. Notice the greater than sign. Why is that? It's because of the local preference. There's a local preference of 200 to use ISP2. There's a local preference of 100 to use ISP1. We've now influenced outbound path selection to prefer the ISP that has more bandwidth. However, we now need to influence inbound path selection. Hosts out on the internet are still coming into us based on the shortest autonomous system path. So let's do this. Let's exaggerate the path via ISP1. And when I say exaggerate, what I mean is, let's say that we want to prepend to that autonomous system path some additional instances of our own autonomous system. Here's what I mean. Let's go back into global configuration mode, and let's create another route map. I'll say route-map, and I'll call this AS path. That's just a name that I made up. That's not some sort of Cisco iOS keyword. And what I'm going to do is set the autonomous system path attribute such that I am prepending additional instances of the local autonomous system. I'm going to add a couple of additional instances. I'll say prepend 65,001 and prepend another instance of 65,001 to the autonomous system path. And I'm only going to apply this route map to ISP1. ISP1 is going to appear to have more autonomous systems to transit in order to get into the enterprise network. Let's go back into router configuration mode for BGP Autonomous System 65,001, and we'll give another neighbor statement pointing to ISP1, neighbor 198.51.100.2, and we're going to apply the route map of AS path, and this time it's going to be in the outbound direction. When I'm sending route advertisements to ISP1, I'm going to be prepending 2 additional instances of my own autonomous system to the AS path. Let's do a soft reset of BGP again. I'll do a clear IP BGP star soft. And let's go out to the internet router and see how it looks coming back in to the enterprise network. Notice before, when we were looking into the enterprise network, we were going via ISP1. The autonomous system path had the same length, whether we went via ISP1 or ISP2. Now we should have updated that such that it's going to be a longer path to go via ISP1. Let's once again do a show IP BGP, and look at this. Now to get to this internal network inside of our enterprise network, the best path is indicated by the greater than sign. It's ISP2. Why is that? Well, now the autonomous system path via ISP2, it's significantly shorter than the path via ISP1. And the reason is I prepended a couple of additional instances of our local autonomous system to the AS path that was being advertised out to ISP1. And that's a very real-world look at how we can troubleshoot a scenario where we have a suboptimal path when an enterprise network is connecting out to more than one ISP. Remember, we need to influence both outbound and inbound path selection.